Hello everyone. Today we will be presenting our project titled AES 256 CBC Symmetric Encryption. That's the secured communication using shared secret keys. So this project was completed as part of our Cryptography for Cybersecurity Practitioner course. My name is Charlotte Awar and I work on this project with my teammates Samrin, Bamed and Hassan under the guidance of Dr. Khaled. In this project, we will show you how encryption, specifically AES 256 in CBC mode, can be used to securely protect communication between users. Now, let us look at why encryption is important. In today's digital world, we are constantly sharing information through messaging apps, banking system, and online platforms. So without encryption, this data could easily be accessed by unauthorized users. That is why encryption helps to protect sensitive information and ensure privacy. For example, in secured messaging, encryption protects private conversation so only the sender and the receiver can read them. On the other hand, banking and finance, it also secure transactions and protect important details like password and account information, as well as the secured information where encryption protects data both when it is stored and when it is being transmitted. So in our project, we simulate secured communication between users using AES 256 CBC, which is one of the strongest and most important trusted encryption standard available for today. We will now be looking at the objectives of our project. So the goal of this lab is to build a fully functional secure messaging system that demonstrates real-world encryption in action. So specifically, our project focused on three main objectives. The first is the encryption and decryption, where we implemented AES to encrypt and decrypt user messages, where we show how data is being protected. And secondly, we ensure that only the intended recipient can read the messages by preventing unauthorized access. That is where confidentiality comes in. And thirdly, we also look at the symmetric encryption, where we demonstrate how a shared secret key is used by both the sender and the receiver to secure communication. So overall, this project helps us to understand how encryption is applied in real-world secured communication system. Before we move forward let us quickly go over some key concepts that are essential to understand our system. First, we have the AES. It is the advanced encryption standard widely used and trusted for secure data encryption. And then we also have the 256 byte key, where it prevents a very large number of possible combinations, making it extremely difficult for attackers to break through the brute force attack. And then we also have the CBC mode, where they link each block of data to the previous one, which helps prevent patterns from appearing in the encrypted output. And then we also have the initialization vector, or the IV, where it adds randomness to the first block by ensuring that even the same messages produce different ciphertext each time. And finally, we add the base 64 encoding, where it converts encrypted data into a readable format so it can be safely transmitted over system that handle text. So all these concepts work together to ensure strong, secure communication in our project. And now that we have covered the fundamental concepts of this, I will hand it over to my teammate Samrim, who will walk us through the implementation and demonstration of our project. Thank you for listening.
I'll explain the tools and technologies we used to build this project. We built everything entirely on in Python, leveraging the PyCryptodome library for cryptographic operations. We chose PyCryptodome because it is an established and added library. And as a cybersecurity practitioner, we know that you should never implement cryptography yourself. Here are the key components we used. Here is a high-level overview of our system workflow. Alice sends a message. She types her plain text message. Then the system encrypts her message with AES 256, turning it into unreadable ciphertext. That ciphertext then gets transmitted over the network. Finally, Bob decrypts it using the same shared key to read the original message. Now I'm going to walk you through our 5 steps encryption process in detail. Step 1, convert to bytes. First, we take the plain text message string and encode it into raw bytes using the UTF-8. Computers work with bytes, not characters. Step 2, add paddings. AES works on fixed size blocks of 16 bytes, so we apply PKCS7 padding to align the bytes of sequences of 16 bytes block boundaries. If the message, for example, is 12 bytes, we add 4 bytes of padding. If it is exactly 16 bytes, we add full blocks of 16 bytes. Step 3, generate random IV. We generate a fresh 16 bytes IV for every single message. This ensures unique ciphertext output every time for even identical messages. Step 4, encrypt with AES 256 CBC. We take the padded bytes and encrypt them using the 256-bit key and then generate IV. Step 5, base 64. Encode output. Finally, we combine the IV and the ciphertext, then encode everything as base 64. The final output looks like this: a compact, transmittable string. Why do we prepend the IV? The IV does not need to be a secret, only unique. By prepending it to the ciphertext before encoding, the receiver can extract it automatically during decryption without needing separate transmission channel.
All right, thanks, Samrin. This is Hassasiyat. I'm gonna continue for the next process, decryption process. Samrin was talking about the encryption, and now I'm gonna talk about decryption. So decryption process is the exact reverse of encryption process. So first, decode base 64. We take the encoded string and convert into back row binary bytes. So that's the first step, and then the second step, extract IV, initial vector, and a cipher. We sliced the first 16 bytes as the IV, and everything after that is the actual ciphertext. So step 3, decrypt. So here we apply advanced encryption standard AES 256 CBC decryption using the shared key and the extracted IV. So both we're gonna use like shared key and then extracted IV. And then next step 4, remove button. So we stripped off the BKCS7 button to recover the original byte sequence. So step 4, we do that. And then step 5, decode to text. So this is the last step, final step. We decode the byte back to a UTF-8 string, and original plain text is stored exactly as the way as it was sent. All right, our simulation model, a real-time secure chat between two users sharing a secret key. So when Alice sends message to Bob, Alice types her message and the system encrypts it with the standard key, and decrypted ciphertext is displayed. So then Bob receives and encrypts it. The original message appears on Bob's screen. So, and then the other side, when the Bob replies to Alice, Bob types his reply, and the system encrypts it with the same shared key, and decrypted reply is displayed, and Alice receives and decrypts it. So the original reply appears on Alice's screen. So session control, the loop continues indefinitely, simulating a live encrypted chat session until the user explicitly types no to exit. So that's how the chat simulation is. All right, here is the sample output of our app. We use the Python, and so we're gonna demonstrate live in the class. So now it's just we're gonna see sample output, but later on we're gonna present in front of class. So as you see on top, it has the name of the app, Secure Chat Simulate, and then also it shows Alice to Bob. That's like the message between going to Alice and Bob, and the date we are recording right now, and we're gonna decode this program, right now. So this screen, as you can see, first step, Alice typed a message. Before that, like the random, you can see key base 64 is here, the sample one, and the one that's like right now system generated. And after that, you can see in the middle, Alice started hello Bob, and then that goes to the encryption process, and then use the key, and then after that, like it's gonna be when it's reached to the Bob receives and decrypts at the same time, you can see the text he received, and then as same as he's going to do text Alice, and then when he says Alice, hello, when Bob says Alice, so you can see that text, and that text goes the same process. It will use like encryption key, and then when it goes to receive Alice, when Alice receives this message, it will decrypt, and then it shows the normal text. So that's how it works, and then you can see if you say this program, it allows you, if you say yes, it will continue. If you say no, it will be like exits out, and then shows who created this program, and then our professor name, Khalid Rabia. We are group 9, and our professor name is Khalid Rabia. So that's it, and then if you press any key, it will disappear this screen. That's it for me right now, and I'm gonna pass it down to the my partner, other Bomet. Kwame will continue after this slide.
Our AES 256 CBC implementation delivered exactly what we expected, which is a strong, reliable confidentiality across all the test messages. This is the result that we got. So the first one is the encryption success. As you guys see, all the messages are encrypted. All the message we tested encrypted and decrypted without any errors or data loss, which is the system worked flawlessly. And also the second one, confidentiality maintained. At no point was any plain text exposed during the transmission, during Alice and Bob composition. Only the ciphertext traveled over the simulated network. The third one is the unique IV per message, which is each message use a fresh initialization vector, which is we verified that even when we send the exact message twice, with the ciphertext is obviously complete different each time. So this prevent from the pattern leaking. So instead of using the same thing, the same password or the same encryption, we use IV initialization vector. So every time it's gonna randomize it. The fourth one is the zero data loss. We don't lose anything. So the description faithfully recovered every original message byte for byte. Nothing was lost or corrupt in the process. So what the AES 256 CBC doesn't protect, we want to be honest with the limitation of our implementation. Obviously, it's a small part of portion that we took. So confidentiality is the only piece of the security puzzle. So here is the critical point with the AES CBC mode encryption data, but also provide no guarantee that the data hasn't been altered in transit. Any attacker could flip bits into ciphertext and cause predictable change in the plain text, and we will never detect it. So this is called a lack of integrity protection, as you guys see here. And furthermore, without any authentication, you cannot verify who sent the message. So we cannot verify what was actually sent. We're not able to see it. The ciphertext could have been modified, or it could have been come from an impersonator. Encryption alone is not fully security. This is a crucial lesson for any cybersecurity practitioner. So all four of them, the no integrity protection, so the data can be silently modified. There's no authentication, so sender identified cannot be verified. Identity, who sent it over, the insecure key sharing, the pre-shared key share, it's going to be unprotected, and vulnerability to tampering, a bit flipping and reply attacks possible. So it's not fully guaranteed. Uh, As you guys see, harden the system. There are a few steps that we can do to harden the system. One of the improvement. So every gap we identify has established a cryptographic remedy. So like this is our upgrade path toward the production ready secure channel. So we have four different kind of production ready secure channel. The first one I would say is the adding HMAC. We could we would have a hash-based message authentication code to detect any tampering without ciphertext before decryption. These provide integrity protection. And the second one is implementing a Diffie-Hellman key exchange. This would eliminate the insecure pre-shared key, establishing a shared secret over untrusted channel. So no key would be ever transmitted directly, which is very secure. And also the third one, we can add a digital signature, which is also very important. So this would bind each message to verify the sender identity, providing non-repudiation and authentication. The fourth one is upgrade AECG-CM, which is the authenticated encryption mode that combine confidentiality and integrity in a single effective primitive, and also the modern standard for secure communication. So this improvement would take our educational project production remedy system, which is a better, I think we can move it to a better forward security. As a conclusion, we have a few key takeaway for anyone who's watching this video. What we built was a working AES 256 CBC encrypted that demonstrate the full real-world encryption cycle and a key setup, IV generation, encryption, transmission, and decryption. So this is what we built. The encryption alone is not enough. Obviously, the true security require confidentiality, integrity, and authentication, or we call them CIA, to working together. The strong confidentiality, also one of them is, which is the AES 256 CBC is proven, and also industry standard cipher for protecting data in reset and transit. Our implementation proved its effectiveness. Also, the security key management, we learned that too, how you store and key exchange as critical as the algorithm itself. So, which is the strongest encryption is useless if the key is exposed. So, we always have to secure our key management. The key lesson also, encryption not alone is not enough. As I said, the true security require the CIA, which is confidentiality, integrity, and authentication working together. One without other leaves vulnerables, which is we exposed to vulnerability. Thank you so much for following along our presentation. Now I can open the floor for discussion. What would you tackle first, the hardened system? What would you add HMAC for integrity? Would you implement Diffie-Hellman for a key exchange? Would you upgrade the to AEC GCM? I invite you to share your thoughts and ask any question if you have about our implementation, about AES encryption in general, or about any of the concepts we discussed today, including the coding that we did. Please go ahead.